Welcome to DEFUNCT. Let's initialize the simulation environment. Set the parameters. 35 warships. A total program cost of $17.5 billion. An average of $500 million per hull. The design objective was absolute coastal dominance, hitting a staggering sprint speed of 45 knots, or roughly 83 kilometers per hour. But here is the critical engineering failure we are dissecting today. When forced to push past 25 knots, these so-called apex predators of the littoral combat zone physically tear their own structural plating apart. We are going to find out exactly why. Initiate the Unreal Engine 5 workspace. Render a turbulent sea state and drop one of these Independence-class Littoral Combat Ships directly into the digital ocean. Now, remove the water physics. Let the vessel hang in the empty void of our 3D grid so we can begin the autopsy. Execute a Boolean cross-section cut along the starboard longitudinal axis. Strip away the outer radar-absorbent shell and make the aluminum 5083 hull plating completely transparent. Zoom in on the primary engineering spaces. What you are looking at is the heart of the beast, the Rolls-Royce MT30 marine gas turbine. It is essentially the exact same core architecture used in the Boeing 777 commercial airliner, but heavily modified to suck in highly corrosive salt air and convert it into pure kinetic violence. We have two of these gas turbines working in tandem with two massive MTU Friedrichshafen diesel engines. Highlight the MT30 output shaft. When running at maximum continuous rating, a single MT30 produces a terrifying 36 megawatts of shaft power. To put that physical force into perspective, imagine strapping the entire power grid output of a small town into a hollow, lightweight aluminum speedboat chassis. That is the fundamental thermodynamic and structural paradox of this vessel. It is an excessive amount of rotational kinetic energy housed inside a fragile exoskeleton. Watch the thermal simulation as the turbines spool up. The combustion chambers reach temperatures exceeding 1,000 degrees Celsius, generating a massive volume of high-velocity exhaust gas that spins the power turbine. The sheer torque generated here is meant to propel 3,000 tons of metal through a substance that is 800 times denser than air. Now, shift the camera down and isolate the drivetrain. Detach the main combining gear and let it float in our 3D workspace. This specific piece of machinery is the absolute mechanical bottleneck of the entire propulsion system. Its job is to take the violent, high RPM rotational energy from the gas turbines and seamlessly merge it with the lower RPM, high torque output from the diesel engines, channeling all that combined kinetic force into the water jets. Run a stress test simulation on the gear teeth. When the ship attempts to accelerate from cruising speed to its 45-knot sprint, the sheer mechanical trauma inflicted on this combining gear is catastrophic. You can see the heat map glowing blindingly white at the points of contact. The sheer stress acting on these carbon steel gears is astronomical. The friction generates so much parasitic heat that the lubricating oil struggles to maintain its viscosity, leading to micro-abrasions along the gear faces. But the combining gear's internal struggle is only a fraction of the fatal flaw. Let us reattach the gear and zoom out to look at the mounting brackets connecting the entire propulsion block to the ship's internal skeletal structure. Here is where the laws of physics issue their death sentence. We are looking at a classic, irreversible metallurgical mismatch. Highlight the drive shafts and the transmission housing. These components are forged from high-tensile steel, engineered to be as rigid and unyielding as statically possible to prevent energy loss during rotation. Now, highlight the surrounding ship frame. The entire hull is constructed from aluminum 5083, an alloy chosen specifically for its ultra-lightweight properties to allow for that 45-knot top speed. Aluminum inherently has a much lower modulus of elasticity compared to steel. What does that mean in the real world? It means the ship's hull is designed to flex, bend, and warp as it slams into ocean waves. Now play the simulation at 25 knots. The aluminum hull is dynamically flexing under the hydrodynamic pressure of the ocean. The hull bends up, but the rigid steel transmission block refuses to bend with it. The result? A catastrophic mechanical conflict. The heavy steel engine mounts act like giant crowbars prying against the soft aluminum framing. Every time the hull flexes in the waves, the unyielding steel engine block concentrates massive torsional loads directly onto the aluminum welds. The engine is literally trying to rip itself out of the ship's body. Let us dive deeper into the metallurgical mismatch. The aluminum 5083 alloy is fantastic for reducing displacement, but it suffers from a fatal flaw known as fatigue limit. Unlike steel, which has a specific fatigue limit below which it will theoretically never fail, regardless of how many times it is bent, aluminum has no defined fatigue limit. Every single microscopic bend, every vibration, every wave impact, cumulatively adds to the degradation of its structural integrity. Over time, failure is a mathematical certainty. It is only a question of when. Now introduce the harmonic vibrations from those 36 megawatt turbines. Render the acoustic and physical shock waves emanating from the combining gear. As the ship pushes past 20 knots, the frequency of the engine vibrations begins to align with the natural resonant frequency of the aluminum hull panels. We are seeing constructive interference. The vibrations amplify. The rigid steel engine mounts are bolted directly to these flexing aluminum stringers. At 25 knots, the opposing forces reach a critical threshold. The ocean compresses the hull inward with thousands of pounds of hydrostatic pressure per square meter, while the immense torque of the propulsion shafts twists the frame in the opposite direction. The rigid steel transmission housing acts as a fixed fulcrum point. The aluminum ribs around it become the lever. The kinetic energy generated by the combustion of marine diesel is actively weaponized against the ship's own exoskeleton. Zoom in on the primary weld seams along the engine bed. Watch the stress map turn from yellow to critical red. The heat-affected zones around the welds, which are already the weakest points in any aluminum structure due to the thermal degradation during construction, begin to experience microscopic grain boundary separation. The metal is literally unzipping itself at the molecular level. This is not battle damage from an anti-ship missile. This is a self-inflicted wound, a fundamental engineering oversight where the pursuit of extreme speed completely disregarded the physical realities of material science. Let us transition the 3D model out of the sterile vacuum and drop it back into the physics simulator. We are going to dial the environmental parameters up to sea state 4. This translates to wave heights of roughly 1.25 to 2.5 meters, with wave periods erratic enough to induce severe pitching and rolling motions. For a traditional blue water warship, this is a mild Tuesday. For the Independence-class Littoral Combat Ship, it is a structural death sentence. Engage the hydrodynamic pressure overlay on the hull. As the vessel accelerates past 20 knots, it attempts to transition from operating as a displacement hull to a planing hull. It is physically trying to climb on top of its own bow wave to achieve that mandated 45-knot sprint speed. But water is incredibly unforgiving. Calculate the wave-making resistance and the dynamic buoyancy shifts. As the hull slams down into the troughs, the sudden deceleration force equates to dropping a 15-ton concrete block from a 3-story building directly onto the deck every 3 seconds. At 25 knots, the bow of the ship is violently slamming into the incoming wave crests. Each collision generates a massive spike of hydrostatic pressure that does not just dissipate, it transfers direct kinetic shock waves straight down the keel and into the fragile aluminum skeletal framing. We are talking about hundreds of thousands of newtons of force repeatedly striking the underbelly of a ship that was built to the weight tolerances of a commercial airliner. Now, shift the camera to the stern and isolate the 4 massive Wärtsilä LJ-160E water jets. When the captain orders maximum throttle, these axial flow impellers spool up, sucking in and violently expelling nearly 500,000 gallons of seawater every single minute. The thrust generated is apocalyptic. But remember the rigid steel transmission block that analyzed earlier? Here is where the trap closes. The water jets are pushing the ship forward from the transom with tens of millions of newtons of force, while the ocean waves are simultaneously hammering the bow backward and upward. The ship's longitudinal bending strength, meaning its ability to resist snapping in half along its entire length, is being tested to its absolute mathematical limits. Zoom in for a macro shot of the hull stringers running alongside the engine room compartment. Activate the stress heat map. The green indicators flash to yellow, then rapidly spike to a blinding, critical red. The sheer kinetic force of the water jets pushing from the rear, combined with the unyielding steel engine mounts refusing to flex, focuses all of the ship's kinetic trauma into the heat-affected zones of the aluminum welds. Watch the molecular structure fail in real time. Microfractures begin to propagate along the grain boundaries of the aluminum 5083 alloy. It starts as a microscopic hairline crack invisible to the naked eye. But as the harmonic vibrations from the 36-megawatt gas turbines synchronize with the rhythmic slamming of the ocean waves, that crack aggressively propagates. It branches out like a spider web of mechanical failure, ripping through the structural plating at 25 knots. The hull is literally splitting open under the sheer violence of its own propulsion. To truly understand the absurdity of this engineering failure, we must place it on the combat comparison scales against the gold standard of the United States Navy, the Arleigh Burke-class guided missile destroyer. Let us pull a 3D wireframe of an Arleigh Burke into the simulation right next to our crippled LCS. The Arleigh Burke is constructed entirely of high-yield steel, specifically HY80, a highly specialized metallurgical material designed to absorb catastrophic kinetic impacts, including the overpressure shock waves from near-miss torpedo detonations. Its hull features a traditional deep V displacement design. When an Arleigh Burke encounters Sea State 4, or even Sea State 6, its heavy steel hull violently slices through the wave crests, and the immense elasticity of the steel allows the entire skeletal structure to bend and absorb the hydrodynamic shock without permanently deforming. The kinetic energy is safely dissipated through thousands of tons of structural mass. Now look back at the LCS floating beside it. By choosing a lightweight, flat-bottomed planing hull made of aluminum, the aerospace designers completely sacrificed the ability to absorb energy. The LCS does not slice through the waves, it skips across them, taking the full kinetic impact of every single wave directly on its fragile chin. The Arleigh Burke bends and survives. The LCS stays rigid where it should not, flexes where it cannot afford to, and inevitably shatters. The destroyer is a warship built for the brutal physical realities of the ocean. The Littoral Combat Ship is a glorified speedboat that looks phenomenal on a computer-aided design screen, but rapidly disintegrates when introduced to the actual physical laws of the natural world. What is the real-world consequence of this catastrophic metallurgical oversight? A complete operational humiliation. The United States Navy was forced to issue a fleet-wide directive explicitly banning these $17.5 billion coastal dominance platforms from exceeding 15 knots in anything rougher than mild sea conditions. Let that grim engineering reality sink in. A fleet of hyper-advanced radar-evading apex predators, heavily marketed on their ability to outrun anything on the water at 45 knots, was legally restricted to a crawling pace of 15 knots. That is drastically slower than most heavy civilian cargo freighters, and arguably slower than a surfaced World War II diesel submarine. At 15 knots, this ship cannot physically perform its required littoral combat missions. It cannot intercept fast attack craft. It becomes a massive, multi-million-dollar sitting duck. The Navy spent $17.5 billion to build 35 hulls, only to realize they had manufactured a fleet of self-destructing aluminum cans that literally crack under the weight of their own horsepower. The design was so fundamentally flawed that the Navy has already begun prematurely decommissioning these vessels, sending billion-dollar combat ships to the scrapyard decades before their intended structural lifespan. This is the ultimate, incredibly expensive lesson in mechanical hubris. You can engineer the most powerful marine turbine on the planet, you can write the most advanced automated targeting software, but you can never, ever cheat the fundamental laws of metallurgy and physics. Welcome to DEFUNCT. If you found this forensic breakdown of mechanical failure insightful, subscribe to the channel, hit the notification bell, and drop a comment below on which catastrophic engineering disaster we should dissect next.